On February 23rd, 1987, an astronomer named Ian Shelton was working at the Las Campanas Observatory in Chile. He was developing a photographic plate of the Large Magellanic Cloud, a small galaxy that orbits our own Milky Way. He noticed a new bright star that wasn't there before. At first, he thought it was a flaw on the plate, but it was real. Shelton had discovered Supernova in 1987. He was one of the first people to witness the violent death of a star. What he saw was the light from an explosion that had happened 168,000 years earlier. For 168,000 years, the light from this cataclysm traveled across the void between galaxies. It finally reached Earth on that February night. The star, a blue supergiant called Sanjulac 69202, had collapsed under its own gravity and then blown itself apart. In that single event, it released an amount of energy equivalent to 100 million times the output of our sun. For a few weeks, this one dying star outshone an entire galaxy of 100 billion stars. For hours before the light arrived, underground detectors in Japan and the United States picked up a burst of neutrinos. These tiny, ghost-like particles had streamed out of the star's collapsing core, passing through the star's outer layers and through space itself almost unimpeded. They were the first signal that something terrible and magnificent had occurred. The universe had put on one of its most violent displays, and for the first time, humanity had the tools to watch it unfold. Number 25, a planet can smash into another planet. An object the size of Mars, traveling at 25,000 miles per hour, can collide with a young planet. The energy released in such an impact would be trillions of times greater than the largest nuclear bomb ever tested. The surface of both bodies would liquefy into a global ocean of magma. A cloud of vaporized rock and debris would be thrown into orbit, eventually coalescing to form a moon. The moon that hangs in our sky is likely the result of such a collision. The leading theory is called the giant impact hypothesis. About 4.5 billion years ago, the early Earth was a very different place. It was still molten and forming. A protoplanet, which scientists have named Theia, was on a collision course with it. Theia was roughly the size of Mars. Its orbit was unstable, and it eventually crashed into Earth. The impact was not head-on. It was a glancing blow. But the energy was immense. It would have vaporized Theia completely and a large portion of Earth's mantle. The cores of the two planets, both made of heavy iron and nickel, would have merged. A massive ring of superheated rock and gas was ejected into orbit around the wounded Earth. For a time, Earth would have had a ring system like Saturn, but made of glowing, molten debris. Over thousands of years, this debris began to clump together. Gravity pulled the pieces into a single large body. This body became our moon. This theory explains a lot of things. It explains why the moon is so large relative to Earth. It explains why the moon has a very small iron core. It was formed mostly from the lighter mantle material of Earth and Theia. It also explains why moon rocks brought back by the Apollo missions have a chemical composition very similar to Earth's crust, but are missing certain volatile elements that would have boiled away in the heat of the impact. We see evidence of these collisions elsewhere. In 2009, NASA's Spitzer Space Telescope observed a young star system called HD 172,555. It found evidence of a recent high-speed collision between two rocky planets. The system was filled with fine dust and silica glass, the kind of material that forms when rock is instantly vaporized and then cools. It was like looking at the immediate aftermath of the event that formed our own moon. These events are a normal, if violent, part of how planetary systems are built. The stability we enjoy is the result of a chaotic and brutal past. A single impact can shatter worlds, create new ones, and set the stage for billions of years of planetary evolution. Number 24. A rogue star can wreck a solar system. There are more rogue stars in our galaxy than there are stars in stable systems. Estimates suggest there could be trillions of these orphan stars ejected from their birthplaces and now drifting through interstellar space. If one passed through our solar system, it would not need to collide with anything to cause a cataclysm. Its gravity alone would be enough. The delicate balance of our solar system would be torn apart. A rogue star is a star that is not gravitationally bound to any galaxy. They are thrown out of their home galaxies during galactic mergers, or by passing too close to a supermassive black hole. They travel through the vast emptiness between galaxies. But within a galaxy, there are also interstellar wanderers. These are stars ejected from their star clusters by gravitational interactions with other, more massive stars. Imagine a star like our Sun, or even a smaller red dwarf, entering our solar system. The first sign would be its gravitational pull on the objects in the Oort cloud. The Oort cloud is a theoretical sphere of icy bodies surrounding our solar system, extending out almost a light year. It is the source of our long-period comets. The gravity of a passing star would disrupt this cloud completely. Or it would send a storm of comets, potentially trillions of them, hurtling into the inner solar system. The resulting bombardment of Earth and the other planets would last for millions of years. It would cause mass extinctions and could potentially sterilize the planet. If the rogue star passed closer through the orbits of the outer planets, the effects would be even more severe. The orbits of Neptune, Uranus, Saturn, and Jupiter would be twisted and warped. They could be thrown into new, highly elliptical orbits. Some could be ejected from the solar system entirely. Jupiter, with its immense gravity, acts as a sort of gravitational shield for Earth, deflecting many comets and asteroids. Or losing Jupiter, or having its orbit changed, would leave Earth much more vulnerable. If the star passed through the inner solar system, it would be the end of everything as we know it. Earth's orbit could be altered. We could be pushed closer to the sun, turning our world into a scorching desert like Venus. Or we could be pushed further away into a permanent ice age. A close enough pass could even strip Earth of its atmosphere and oceans. The chances of a direct hit are minuscule, but the chances of a disruptive flyby are not zero. Over the vast timescales of the galaxy, such events are inevitable. Somewhere right now, a stable solar system is likely being torn apart by an unseen wandering star. Number 23. A magnetar can release more energy in a second than the sun does in a year. A magnetar is a type of neutron star with an incredibly powerful magnetic field. This field is about a quadrillion times stronger than Earth's. It is so strong that it distorts the very shape of the atoms on the star's surface. If you were within 1,000 kilometers of a magnetar, its tidal forces would stretch you into a thin string of atoms. The magnetic field would rip the electrons from your body. Magnetars are born from the same supernova explosions that create other neutron stars, but only in specific conditions that are not fully understood. They are a rare and extreme form of matter. A neutron star is already an extreme object. It's the collapsed core of a massive star, packing the mass of our sun into a sphere only about 12 miles across. A single teaspoon of neutron star material would weigh 1 billion tons. A magnetar is this, but with a magnetic field of unimaginable power. This immense magnetic field is not stable. The star's crust is under constant, incredible stress from the shifting and twisting magnetic field lines. Sometimes the crust cracks. This is a starquake. A starquake on a magnetar is a cataclysmic event. It releases a burst of high-energy X-rays and gamma rays. These are called soft gamma repeaters. On December 27, 2004, a giant flare erupted from a magnetar named SGR 1806-20. This magnetar is located about 50,000 light-years from Earth on the other side of the galaxy. In just 1/10 of a second, the flare released more energy than our sun has emitted in the last 100,000 years. The radiation was so intense that it saturated the detectors on multiple satellites. It bounced off the moon and was detected by instruments pointing in the opposite direction. It partially ionized Earth's upper atmosphere, disrupting radio communications. This happened from 50,000 light-years away. If a magnetar flare like that were to happen within a few hundred light-years of Earth, it would be devastating. The initial burst of gamma rays would strip away our ozone layer, leaving the surface exposed to deadly ultraviolet radiation from our own sun. It would cause widespread radiation sickness and could trigger a mass extinction event. The sheer energy hitting the atmosphere could cause chemical reactions that would darken the sky and change the climate. There is a theory that a past mass extinction event on Earth might have been caused by a nearby gamma ray burst, possibly from a magnetar. These objects are tiny, but their power is galactic in scale. Number 22, a star can explode as a hypernova. A standard supernova is the explosion of a massive star. A hypernova is something else entirely. It is the death of a truly colossal star, one that is at least 30 to 40 times the mass of our sun. A hypernova can be over 100 times more powerful than a regular supernova. When one of these giants dies, it doesn't just explode. It creates a collapsar. The process begins when the star runs out of fuel. Its core, unable to support the immense weight of the outer layers, collapses. But because the star is so massive, the core collapse doesn't stop to form a neutron star. It keeps going, collapsing all the way down into a black hole. This newly formed black hole is at the heart of the dying star. The star is also rotating very rapidly as the material from the star's outer layers falls towards the new black hole. It forms a spinning disk of superheated matter around it. This is called an accretion disk. The black hole begins to feed on this disk, swallowing matter at an incredible rate. But not all of the matter falls in. The intense magnetic fields and energy from the accretion disk can launch two powerful jets of material away from the black hole's poles. These jets travel at nearly the speed of light. These jets then blast their way out through the rest of the collapsing star. They are like cosmic blowtorches tearing through the star's layers from the inside out. When they finally burst free, they release an immense, focused beam of gamma rays. This is what we observe as a long-duration gamma ray burst, one of the most energetic phenomena in the universe. The rest of the star is then blown apart in the hypernova explosion. A hypernova seeds the surrounding space with heavy elements. The extreme conditions in the explosion are thought to be one of the primary places where elements heavier than iron, like gold and platinum, are created. The star's death creates the raw materials for new stars and planets. If a hypernova were to occur within a few thousand light years of Earth and its jets were pointed directly at us, the consequences would be catastrophic. The gamma ray burst would be like a cosmic death ray. The initial flash of radiation would destroy our ozone layer in seconds. This would expose the surface to the full force of the sun's UV radiation, killing off plankton in the oceans and disrupting the entire food chain. The radiation would also cause atmospheric changes, leading to acid rain and a rapid cooling of the planet. It would be an extinction event on a scale we have never seen. Thankfully, these events are rare, and the chances of one being close and aimed at us are very, very low. Number 21. A black hole can rip a star apart. A star that wanders too close to a supermassive black hole is doomed. The black hole's gravity is so intense that it exerts a much stronger pull on the near side of the star than on the far side. This difference in gravitational force is called a tidal force. The same forces cause tides on Earth, but on a cosmic scale they become instruments of destruction. This event is called a tidal disruption event, or TDE. As the star gets closer to the black hole, the tidal forces stretch it. It gets pulled into a long, thin shape, like a piece of spaghetti. This process is called spaghettification. The star is drawn out into a stream of gas. It ceases to be a star. It becomes a river of its own matter flowing towards the black hole. Some of this material is flung out into space on a wide trajectory. but about half of the star's mass is captured by the black hole and begins to orbit it. It forms a bright, hot accretion disk. As the gas in this disk spirals into the black hole, it heats up to millions of degrees due to friction. This superheated gas emits a brilliant flare of X-ray and ultraviolet radiation. This flare can be seen from millions of light years away. For a few months, the normally quiet center of a galaxy can light up, signaling that its central black hole is having a meal. Astronomers have observed dozens of these events. In 2019, they watched a TDE happen in a galaxy 375 million light years away. They were able to observe the star being shredded and the subsequent flare of light as the material was consumed. By studying the light from these events, scientists can learn about the properties of supermassive black holes, like their mass and spin. For the star, it is a complete and violent end. For the black hole, it is a brief period of activity. These events are a key way that supermassive black holes grow over cosmic time. They are not just passive objects sitting at the center of galaxies. They are active participants shaping their environment by consuming anything that gets too close. A galaxy's center is a dangerous place. The monster that lurks there is usually quiet, but when it feeds, the entire galaxy can see the flash. Number 22. Neutron stars can merge in a kilonova. A neutron star is the dense remnant of a supernova. A binary system can contain two of these objects orbiting each other. Over millions of years, they spiral closer together. They lose energy by emitting gravitational waves, ripples in the fabric of space-time itself. As they get closer, they orbit faster and faster, whipping around each other hundreds of times per second in the final moments. Then they collide. The merger of two neutron stars is one of the most violent events in the universe. It creates an explosion called a kilonova. A kilonova is about 1,000 times brighter than a standard nova, an explosion on a white dwarf, but not as bright as a supernova. But its significance is far greater than its brightness. The collision is cataclysmic. Two objects, each with more mass than the sun, crushed into the size of a city, slam into each other at a significant fraction of the speed of light. The result is a maelstrom of energy and exotic matter. For a brief moment, a single hypermassive neutron star might form before collapsing into a black hole. Or a black hole might form instantly. During this merger, a huge amount of neutron-rich material is ejected into space. This material undergoes a process called R-process nucleosynthesis. In the extreme heat and density of the collision, neutrons are rapidly captured by atomic nuclei, building up heavy elements. This is where most of the universe's gold, platinum, uranium, and other elements heavier than iron are created. The gold in a wedding ring was forged in the collision of two dead stars. On August 17, 2017, the LIGO and Virgo gravitational wave observatories detected a signal named GW1. It was the unmistakable signature of two neutron stars merging. Seconds later, space-based telescopes detected a short gamma-ray burst from the same patch of sky. Astronomers around the world pointed their telescopes to the source, a galaxy 130 million light-years away. They saw the afterglow of the kilonova. They watched it fade over the following days and weeks. By analyzing the light, they found the chemical fingerprints of heavy elements like gold and strontium. It was the first time we had ever witnessed the creation of these elements in real time. It confirmed that these violent mergers are the universe's precious metal factories. Number 19, an active galactic nucleus can sterilize its host galaxy. At the center of most large galaxies, including our own Milky Way, lies a supermassive black hole. These black holes can have masses of millions or even billions of times that of our sun. Most of the time they are dormant, but if a large amount of gas and dust falls into them, they can turn on and become an active galactic nucleus, or AGN. The most luminous type of AGN is a quasar. When a black hole becomes active, it is surrounded by a massive, incredibly hot accretion disk of swirling matter. As this material is torn apart and heated by friction on its way to the event horizon, it shines with unimaginable brilliance. A single quasar can outshine its entire host galaxy of hundreds of billions of stars, and it can be seen from across the observable universe. The light we see from the most distant quasars left them when the universe was less than 1 billion years old. This intense radiation is a form of galactic feedback. It pushes back against the gas and dust in the galaxy. A powerful AGN can launch winds of particles that travel at a substantial fraction of the speed of light. These winds can sweep through the galaxy, heating up the interstellar gas and blowing it out of the galactic disk entirely. This has a profound effect on the galaxy's evolution. Star formation requires cool, dense clouds of gas to collapse under gravity. If an AGN heats up and expels all this gas, it effectively shuts down star formation in the galaxy. The galaxy can no longer create new stars. It becomes a red and dead galaxy, full of old red stars, with no new blue ones being born. The central monster has sterilized its own home. Furthermore, a quasar emits not just visible light, but a huge amount of X-rays and gamma rays. If a planet in that galaxy were to be exposed to this radiation, its atmosphere could be stripped away. Any life on its surface would be scoured away. The AGN acts like a giant sterilization lamp for its entire galaxy. Our own Milky Way's central black hole, Sagittarius A, is currently quiet, but there is evidence that it was much more active in the past. It might turn on again in the future if a large gas cloud wanders too close. A cataclysm at the galactic core can decide the fate of trillions of worlds. Number 18, galaxies can collide and merge. Galaxies are not static islands of stars. They move through space, pulled by the gravity of their neighbors and the underlying structure of dark matter. Sometimes their paths cross. When two galaxies collide, it is one of the most spectacular and prolonged cataclysms in the cosmos. The process can take hundreds of millions of years to complete. Despite the name, a galactic collision is not like a car crash. The stars within the galaxies are very far apart. It is extremely unlikely that any two stars will actually hit each other. Instead, the collision is a gravitational battle. The two galaxies pass through each other like ghosts, but their immense gravity distorts and reshapes them. As they merge, vast clouds of gas and dust within each galaxy are compressed. This compression triggers a massive wave of star formation called a starburst. For a time, the merging galaxy blazes with the light of millions of newly born, hot blue stars. These new stars live fast and die young, exploding as supernovae and enriching the new galaxy with heavy elements. The tidal forces pull long streamers of stars and gas out of the galaxies, creating beautiful and chaotic shapes. These are called tidal tails. The galaxies may pass through each other several times, getting more and more distorted with each pass, before they finally settle down and merge into a single, larger galaxy. The supermassive black holes at the center of each galaxy will also eventually find each other. They will begin to orbit one another, forming a binary supermassive black hole system. Over millions of years, they will spiral together, releasing powerful gravitational waves before merging in a final, violent event that sends a gravitational shockwave across the universe. This is not a hypothetical scenario. We see galaxies in all stages of collision and merger throughout the universe. The antennae galaxies are a famous example of two galaxies currently in the process of merging. And our own Milky Way is on a collision course with our nearest large neighbor, the Andromeda Galaxy. In about 4.5 billion years, they will begin to merge. The night sky of a future Earth will be a spectacular sight, as the band of Andromeda grows to fill the view. The collision will likely throw our solar system into a new, different orbit within the resulting galaxy, which some astronomers have nicknamed Milkomeda. The familiar patterns of our galaxy will be gone, replaced by a new, larger, and more chaotic structure born from the slow gravitational violence of a cosmic dance. Number 17, a Type Ia supernova can obliterate a nearby planet. A white dwarf is the dead core of a sun-like star. It's an object about the size of Earth, but with the mass of the sun. It no longer generates energy through fusion, it just slowly cools over trillions of years. But if that white dwarf is in a binary system with another star, it can have a second, much more violent life. If the companion star is a normal star like a red giant, the white dwarf's intense gravity can pull material, mostly hydrogen and helium, from its partner. This material builds up on the surface of the white dwarf. As the layer of stolen material gets thicker and hotter, it can eventually reach a temperature and pressure where it ignites in a runaway thermonuclear reaction. This is called a nova. It's a powerful explosion, but it only blows off the surface layer, leaving the white dwarf intact to start the process again. A type Ia supernova is far more destructive. It happens when the white dwarf pulls so much material from its companion that its total mass approaches a critical limit, about 1.44 times the mass of our sun. This is known as the Chandrasekhar limit. At this mass, the pressure in the core of the white dwarf becomes so great that it can no longer support itself. The core temperature skyrockets and carbon fusion ignites everywhere at once. The result is a thermonuclear bomb the size of a planet. The entire white dwarf is consumed in a fraction of a second. Unlike a core collapse supernova, it leaves nothing behind. No neutron star, no black hole. The star is completely obliterated. The energy released is immense and, importantly, very consistent. Because they all explode at roughly the same mass, type Ia supernovae all have about the same peak brightness. This makes them incredibly useful as standard candles for measuring cosmic distances. It was by observing these explosions in distant galaxies that astronomers discovered the accelerating expansion of the universe. But to be near one would be a death sentence. A type Ia supernova releases a flood of deadly gamma rays and X-rays. Then comes the shockwave and the debris from the vaporized star, traveling at a few percent of the speed of light. Any planet in the system would be scoured clean of its atmosphere and its surface sterilized. If the planet were close enough, it could be completely vaporized. The explosion of a dead star can be one of the brightest and most destructive events in the universe. Number 16, the Big Bang was the most violent event in history. The universe, as we know it, began in an event of unimaginable violence and energy. This was the Big Bang. It was not an explosion in space, but an explosion of space itself. About 13.8 billion years ago, all the matter and energy in the observable universe was concentrated into a point of infinite density and temperature, a singularity. Then it began to expand. In the first fraction of a second, the universe underwent a period of exponential expansion called inflation. It grew from smaller than an atom to larger than a galaxy in an instant. The laws of physics as we know them did not apply. The universe was a hot, dense soup of fundamental particles and radiation. As the universe expanded, it cooled. Quarks combined to form protons and neutrons. A few minutes after the Big Bang, the universe was cool enough for these protons and neutrons to fuse into the first atomic nuclei, mostly hydrogen and helium. This is called Big Bang nucleosynthesis. For the next 380,000 years, the universe was still a hot, opaque plasma. Photons of light were constantly scattering off free electrons, unable to travel very far. The universe was a glowing fog. After about 380,000 years, the universe cooled enough for electrons to combine with nuclei to form the first neutral atoms. This event is called recombination. Suddenly, the photons were free to travel through space unimpeded. The universe became transparent for the first time. The light from this moment is still traveling through the universe today. It has been stretched by the expansion of space into microwaves, and we observe it as the cosmic microwave background radiation, the afterglow of the Big Bang. The Big Bang was not just a creative event, it was the ultimate cataclysm. The conditions of energy, temperature, and pressure at the beginning are beyond anything that has happened since. Every structure we see today, stars, galaxies, clusters of galaxies.com, is a result of tiny quantum fluctuations in that initial state, magnified by inflation, and then slowly shaped by gravity over billions of years. The entire history of the cosmos is the story of the universe cooling down and calming down from its violent birth. Number 15, 2. Black holes can merge and shake spacetime. A single black hole is a region of spacetime where gravity is so strong that nothing, not even light, can escape. But black holes can exist in binary pairs orbiting each other. Like neutron stars, they radiate energy in the form of gravitational waves. This causes them to lose orbital energy and they spiral inward closer and closer together. The final moments of a black hole merger are a cosmic spectacle of pure physics. The two black holes, each a perfect sphere of warped spacetime, orbit each other at speeds approaching the speed of light. They distort the fabric of spacetime around them so violently that it's like two massive bowling balls swirling in a rubber sheet just before they collide. When they finally merge, they form a single, larger black hole. This new black hole is not perfectly spherical at first. It's a distorted, wobbling object that quickly rings down into a stable state like a bell being struck. In this final merger and ringdown phase, an enormous amount of energy is released in the form of gravitational waves. For a brief moment, the power radiated by a black hole merger can be greater than the power radiated as light by all the stars in the observable universe combined. This energy is not in the form of light or heat. It's pure gravitational energy, a tsunami of ripples in space-time itself, expanding outward at the speed of light. On September 14, 2015, the LIGO detectors made the first ever directed detection of gravitational waves. The signal, named GW150-15150, came from the merger of two black holes, one about 36 times the mass. They merged to form a new black hole of about 62 solar masses. The missing 3 solar masses were converted directly into gravitational wave energy, according to Einstein's E=mc². This single event, which lasted only a fraction of a second, released 50 times more energy than all the stars in the universe combined. The ripples traveled for 1.3 billion years to reach Earth. By the time they got here, the distortion they caused was minuscule, less than the width of a proton. But the incredibly sensitive LIGO instruments detected it. It was a new way of seeing the universe, not with light, but with gravity itself. It opened a window onto the most violent and energetic events the cosmos has to offer. Number 14, superluminal jets are cosmic particle cannons. Many of the most violent events in the universe, like the formation of a black hole in a hypernova or the activity of a quasar, produce powerful jets of plasma. These jets are streams of charged particles like electrons and protons accelerated to incredible speeds by intense magnetic fields. They are fired out from the poles of the rotating central object like a black hole or a neutron star. These jets travel at speeds that are a very large fraction of the speed of light. They can be 99.9% the speed of light or even faster, because they are moving so close to the ultimate cosmic speed limit, relativistic effects become significant. From our perspective, they can sometimes appear to be moving faster than light. This is an optical illusion called superluminal motion. It happens because the jet is moving towards us at such a high speed that it almost keeps up with the light it is emitting. This makes its apparent motion across the sky seem faster than is physically possible. These jets are colossal. The jets from an active galactic nucleus can extend for hundreds of thousands of light years, far beyond the confines of the host galaxy itself. They blast through the intergalactic medium, heating it up and carving out huge cavities. They are like cosmic particle cannons, firing beams of energy across intergalactic distances. When one of these jets is pointed directly at Earth, we see it as a blazar. A blazar is an incredibly bright and variable source of radiation. Because we are looking straight down the barrel of the jet, the radiation is Doppler boosted, making it appear much brighter and more energetic than it would if viewed from the side. The power of these jets is hard to comprehend. They carry away a significant fraction of the energy from the central engine that creates them. They can shape the evolution of entire galaxies by regulating star formation. They are also responsible for accelerating cosmic rays, high-energy particles that travel through the universe to energies far beyond what we can achieve in particle accelerators on Earth. These jets are a stark demonstration of how the most extreme physics in the universe, happening in the tiny region around a black hole, can have consequences on the largest possible scales. Number 13, a gamma ray burst is the most luminous explosion known. A gamma ray burst, or GRB, is a brief, intense flash of gamma radiation from a distant galaxy. For the few seconds or minutes that it lasts, a GRB can outshine the entire rest of the universe in gamma rays. They are the most luminous electromagnetic events known to occur in the universe. There are two main types of GRBs. Short-duration GRBs last for less than 2 seconds. We now know that these are caused by the merger of two compact objects, like two neutron stars or a neutron star and a black hole. The kilonova explosion is accompanied by a short, intense burst of gamma rays fired out in jets. Long-duration GRBs last from a few seconds to several minutes. These are caused by hypernova explosions, the death of extremely massive stars. As the star's core collapses into a black hole, relativistic jets blast their way out of the star, creating the gamma ray burst. GRBs are so powerful that we can see them from across the observable universe. The most distant GRB ever detected, GRB 90,423, came from an event that happened just 630 million years after the Big Bang. We were seeing the death of one of the very first stars. The energy of a GRB is not radiated equally in all directions. It is focused into two narrow beams or jets. This means that for every GRB we see, there are hundreds more that we miss because their jets are not pointed at us. But it also means that if you are in the path of one of these jets, you receive a much more intense dose of radiation. A GRB from within our own galaxy, if it were aimed at Earth, would be an extinction-level event. The gamma rays would not penetrate the atmosphere to the ground, but they would trigger chemical reactions in the upper atmosphere that would destroy the ozone layer. This would leave the surface exposed to deadly ultraviolet radiation from the sun. It would also create nitrogen oxides that would cause a dark planet-wide smog and acid rain. Some scientists have proposed that the Ordovician-Silurian extinction event, 450 million years ago, may have been caused by a GRB. The pattern of extinction seems to fit with what we would expect from such an event. GRBs are a reminder that the universe is full of random high-energy events that can have profound consequences for life, even from thousands of light years away. Number 12, galactic cannibalism is a common occurrence. Large galaxies grow by eating smaller ones. This process is called galactic cannibalism. Over billions of years, the gravity of a large galaxy, like our Milky Way or Andromeda, pulls in smaller dwarf galaxies that are in orbit around it. These smaller galaxies are then tidally disrupted and absorbed. Their stars and gas are added to the larger galaxy. This is not a gentle process. As the dwarf galaxy is pulled apart, it leaves behind long streams of stars called stellar streams. These streams can be seen wrapping around the larger galaxy like cosmic spaghetti. Astronomers have mapped dozens of such streams in the Milky Way and Andromeda. They are the fossil evidence of past meals. They tell us about the history of our galaxy's formation. The Gaia Space Telescope has been instrumental in discovering this history. By precisely measuring the positions and motions of billions of stars, Gaia has allowed astronomers to identify groups of stars that are moving together in coherent streams, even though they are spread across the sky. They have been able to reconstruct the orbits of the dwarf galaxies that were destroyed to create these streams. One of the most significant merger events in the Milky Way's history was with a dwarf galaxy, now called Gaia Enceladus. This merger happened about 10 billion years ago. It was a major event that puffed up the Milky Way's disk and created a large part of its stellar halo, the diffuse sphere of old stars that surrounds the main disk. This process is still happening. The Sagittarius dwarf spheroidal galaxy is currently in the process of being torn apart and consumed by the Milky Way. Its stars are being stripped away and are forming a massive stream that wraps around our entire galaxy. In the distant future are other satellite galaxies. The Large and Small Magellanic Clouds will also likely be consumed. Galactic cannibalism is a fundamental part of the hierarchical model of galaxy formation. This model says that large structures are built up from the merger of smaller ones. The universe started with small protogalaxies, and over cosmic time they merged to form the giant galaxies we see today. The violence is slow and gravitational, playing out over eons, but it is relentless. The cosmic food chain is real, and our galaxy is one of the predators. Number 11. The Great Attractor is pulling our galaxy towards it. Our galaxy, the Milky Way, is not sitting still. It is moving through space at about 600 kilometers per second, or 1.3 million miles per hour. But its motion is not just due to the expansion of the universe. There is something pulling on us. Our galaxy, the Andromeda Galaxy, and the other members of our local group of galaxies are all being pulled towards a specific point in space. This point is called the Great Attractor. The Great Attractor is a gravitational anomaly located about 150 to 250 million light-years away from us, in the direction of the constellations Hydra and Centaurus. It is not a single object, but a vast concentration of mass. For a long time, it was a mystery. It lies in a region of the sky called the Zone of Avoidance, where the dust and stars of our own Milky Way's disk block our view of distant galaxies. Through infrared and radio observations, which can penetrate the dust, astronomers have been able to map out the region. They found a massive supercluster of galaxies, the Laniakea supercluster, of which our own Virgo supercluster is just an outlying tendril. The Great Attractor seems to be the gravitational center of this colossal structure. Laniakea contains about 100,000 galaxies and stretches over 500 million light-years. The pull of the Great Attractor is a subtle long-range cataclysm. It is the force of gravity acting on the largest scales. All the galaxies in our part of the universe are falling towards this central point. It is a slow-motion cosmic pile-up that will take billions of years to unfold. The individual galaxies are like raindrops flowing into streams, the streams into rivers, and all of it flowing towards a single massive basin. This is a visible manifestation of the cosmic web, the large-scale structure of the universe. The universe is not uniform. Matter, both normal and dark, is arranged in a vast network of filaments, sheets, and nodes. And galaxies form along these filaments and are drawn towards the nodes, which are the massive clusters and superclusters. The Great Attractor is our local node. Our ultimate fate is to be drawn into this cosmic traffic jam, to merge with the other galaxies and become part of an even larger megastructure. It is a form of violence that is quiet, patient, and inescapable. Number 10, dark matter annihilation could be a source of high-energy radiation. About 85% of the matter in the universe is not the normal atomic matter that we are made of. It is a mysterious, invisible substance called dark matter. We know it exists because we can see its gravitational effects on stars and galaxies. And galaxies rotate faster than they should based on the amount of visible matter they contain. The extra gravity holding them together comes from a vast halo of dark matter. We don't know what dark matter is. One of the leading theories is that it is made of a new type of fundamental particle, a weakly interacting massive particle, or WIMP. These particles would not interact with light, which is why they are dark. They would only interact through gravity and the weak nuclear force. If this theory is correct, then in places where dark matter is very dense, like at the center of galaxies or in the cores of dwarf galaxies, these WIMP particles could collide with each other. When a WIMP particle and its antiparticle meet, they would annihilate each other. This annihilation would produce a shower of other more familiar particles, including high-energy gamma rays. This provides a potential way to detect dark matter indirectly. We can look for a mysterious excess of gamma rays coming from regions where we expect dark matter to be concentrated. Telescopes like the Fermi Gamma Ray Space Telescope have been searching for such a signal. There have been some intriguing hints, like a slight excess of gamma rays from the center of our own galaxy, but no definitive discovery has been made yet. If dark matter annihilation happens, it represents a hidden form of cataclysmic event. It is a constant low-level release of energy happening throughout the universe wherever dark matter is dense enough. It is the slow, quiet self-destruction of the universe's most common form of matter. You know, if the annihilation rate were higher, or if there were dense clumps of dark matter nearby, it could be a source of dangerous radiation. The invisible scaffolding of the universe might not be entirely benign. Number 9, a rogue black hole could enter our solar system. Black holes are not all supermassive and anchored at the centers of galaxies. There should also be millions of smaller stellar mass black holes drifting through the Milky Way. These are the remnants of massive stars that died long ago. Like rogue stars, these black holes can be ejected from their birthplaces by gravitational interactions or the kick from a supernova explosion. They wander the galaxy as dark, silent predators. A rogue black hole entering our solar system would be the ultimate disaster. A stellar mass black hole with a mass of maybe 10 times that of our sun would have an event horizon only about 60 kilometers in diameter. It would be completely invisible. We would not see it coming. The first and only warning would be its gravitational influence. As it approached, we would see its effects on the orbits of the outer planets. Comets from the Oort cloud would be sent streaming into the inner solar system. The orbits of Neptune, Uranus, and the other planets would become chaotic. As it got closer, it would be a gravitational wrecking ball. If it passed through the solar system, it could eject planets, including Earth, into interstellar space. A planet ejected from its star would become a cold, dark orphan world. Any life on its surface would freeze. Or it could perturb Earth's orbit, sending us into the sun or into a highly elliptical orbit that would cause extreme temperature swings. If we were unlucky enough to have a close encounter, the tidal forces would be immense. The black hole would rip the Earth apart, the planet would be spaghettified, torn into a stream of rock and magma that would fall into the black hole, creating a brief, bright flare as it was consumed. The chances of this happening are astronomically small. Space is vast, and these objects are rare and tiny. But it is not impossible. There are likely thousands of these dark wanderers in our galactic neighborhood. The universe contains threats that are not only powerful, but also completely invisible until it is too late. Number 8, the late heavy bombardment resurfaced the early Earth. For hundreds of millions of years, the early solar system was a shooting gallery. After the planets formed, there was a huge amount of leftover debris, asteroids, comets, and planetesimals. From about 4.1 to 3.8 billion years ago, there was a period of intense asteroid and comet impacts called the Late Heavy Bombardment. The cause of this bombardment is thought to be a shift in the orbits of the giant planets Jupiter and Saturn. As they migrated to their current positions, their immense gravity destabilized the asteroid belt and the Kuiper belt, sending a massive wave of debris careening into the inner solar system. The Earth, Moon, Mars, Venus, and Mercury were all pummeled by these impacts. The surface of the Moon is the best record we have of this period. Its ancient, heavily cratered highlands are a testament to this violent era. The Earth would have experienced even more impacts because of its larger size and gravity. But on Earth, the craters have been erased by billions of years of erosion, plate tectonics, and volcanic activity. The impacts during this time were of a scale we can barely imagine. There were likely thousands of impacts from asteroids over 10 miles wide, the size of the one that killed the dinosaurs. There would have been dozens of impacts from objects hundreds of miles wide. An impact of that scale would be a global cataclysm. It would vaporize a huge section of the crust and boil the oceans. The atmosphere would be filled with vaporized rock, creating a superheated greenhouse effect that would last for thousands of years. The surface of the planet would have been repeatedly sterilized. It is a paradox that life on Earth seems to have started around this same time, or shortly after. Some theories suggest that while the bombardment would have been destructive to any surface life, it might have actually helped life get started. The impacts could have delivered water and organic molecules to the early Earth. The immense heat from impacts could have driven chemical reactions in hydrothermal systems deep underground or in the oceans, creating environments where life could emerge, safe from the surface chaos. The same violence that repeatedly destroyed the world's surface may have also delivered the ingredients and created the conditions for life's origin. Number 7, star-to-star collisions happen in dense clusters. In the normal disk of a galaxy, stars are incredibly far apart. The nearest star to our sun is over 4 light-years away. The chances of a direct collision are virtually zero. But in the crowded centers of globular clusters, the situation is different. A globular cluster is a dense spherical collection of hundreds of thousands or even millions of old stars. They are tightly bound by gravity. In the core of a globular cluster, the density of stars can be thousands of times greater than in our solar neighborhood. Here, stellar collisions are not just possible, they are a key part of the cluster's evolution. When two stars collide, the outcome depends on their masses and their impact speed. A glancing blow might just strip some material from each star, but a head-on collision is a truly violent merger. The two stars become a single, larger, and much more massive star. These collision products are called blue stragglers. They are a puzzle in globular clusters because they appear to be much younger and bluer hotter than the other stars in the cluster, which are all old. The collision essentially gives the stars a new lease on life. The merger mixes their fuel and creates a more massive star that burns hotter and brighter, making it look like a young star in an ancient population. These collisions can also lead to more exotic outcomes. A collision involving a neutron star or a white dwarf can trigger a powerful explosion or create a rapidly spinning pulsar. The dense cores of globular clusters are like cosmic particle accelerators, creating strange stellar objects that would be rare elsewhere. The collision itself would be a spectacular event. Two suns merging would release a tremendous amount of energy. Any planets orbiting those stars would be destroyed, their orbits catastrophically disrupted before being consumed by the new, larger star. Life in a globular cluster would be precarious, living under the constant threat of a neighbor star suddenly and violently merging with your own. Number 6. A supernova can create a pulsar wind nebula. When a massive star explodes in a core collapse supernova, it can leave behind a neutron star. If this neutron star is highly magnetized and rotating rapidly, it is called a pulsar. A pulsar is like a cosmic lighthouse. It has powerful magnetic poles that emit beams of radiation. As the star spins, these beams sweep across space. If one of the beams points towards Earth, we see it as a regular pulse of radio waves or other radiation. A young, energetic pulsar can create a phenomenon called a pulsar wind nebula. The pulsar's rapid rotation and intense magnetic field generate a powerful wind of charged particles, mostly electrons and positrons, that flow away from the star at nearly the speed of light. This wind crashes into the slower-moving debris from the original supernova explosion. The result is a shock wave that heats the particles and causes them to glow brightly in X-rays and other wavelengths. The pulsar wind nebula is a beautiful, ghostly bubble of high-energy particles powered by the spinning dynamo at its center. The most famous example is the Crab Nebula. It is the remnant of a supernova that was observed by Chinese astronomers in the year 1054. At its heart is the Crab pulsar, a neutron star spinning 30 times per second. The pulsar's wind powers the intricate filamentary structure of the nebula we see today. The nebula is a scene of constant violent activity. The 10th ray images from the Chandra Observatory show wisps and jets of material moving and changing on timescales of days. We are watching the shock waves from the pulsar wind propagate through the supernova remnant in real time. A pulsar wind nebula is a long-lasting cataclysm. The initial supernova is the main event, but the pulsar left behind continues to pump a huge amount of energy into its surroundings for thousands of years. It shapes the remnant of its own birth explosion, creating a complex and dynamic environment. It's a testament to the fact that even after a star dies, its corpse can continue to be a source of immense power and violence. Number 5, the heat death, is the slowest cataclysm imaginable. Not all cataclysms are fast and explosive. Some are slow, quiet, and inevitable. The theory of the heat death of the universe describes a possible ultimate fate where the universe ends in a state of maximum entropy. There'd be a slow, grinding descent into darkness and cold. This scenario assumes that the universe will continue to expand forever. As it expands, the matter and energy within it become more and more spread out. The universe becomes colder and more dilute. The process would unfold over timescales that are almost beyond human comprehension. First, star formation will cease. In about 1 trillion years, all the gas and dust needed to form new stars will have been used up or blown away. The last generation of stars will be small, dim red dwarfs. They burn their fuel very slowly. They will continue to shine for tens of trillions of years, but eventually, even the red dwarfs will burn out. They will become cold, dead white dwarfs. The universe will become dark, populated only by the remnants of stars, white dwarfs, neutron stars, and black holes. The planets that once orbited them will be frozen, lightless worlds. Over even longer timescales, on the order of googolls of years, a 1 followed by 100 zeros, quantum mechanics predicts that even these stellar remnants will decay. The protons might decay, causing matter as we know it to dissolve into a bath of radiation and light particles. The black holes will also eventually evaporate through a process called Hawking radiation. Small black holes will evaporate first, followed by larger and larger ones. Supermassive black holes at the centers of galaxies will take an unimaginable amount of time to disappear, but they too will eventually vanish in a final, faint flash of particles. After the last black hole has evaporated, the universe will be almost perfectly empty. It will be a cold, dark, and uniform soup of photons, neutrinos, and a few stray electrons and positrons, all separated by vast distances. There will be no structure, no change, no life. All the energy will be so spread out that no useful work can be done. This is the state of maximum entropy. The universe will have reached its final, quiet, and eternal state of equilibrium. It is the ultimate cataclysm, not of fire, but of ice. Not a bang, but a slow, silent fade to nothing. Number 4, the Big Rip would tear the universe apart. The discovery that the expansion of the universe is accelerating led to the idea of dark energy. This is a mysterious form of energy that seems to be inherent to space itself, pushing everything apart. If the nature of dark energy is a certain way, it could lead to a far more violent end than the heat death. This end is called the Big Rip. In the Big Rip scenario, the repulsive force of dark energy grows stronger over time. This is what is known as phantom dark energy. At first, the effects are subtle, the acceleration of the universe's expansion gets faster and faster, but as time goes on, the repulsive force of dark energy starts to overwhelm gravity on smaller and smaller scales. Billions of years from now, it would become strong enough to pull apart the largest structures in the universe. Clusters of galaxies would be unbound, and the individual galaxies would fly apart. Then, as the end approaches, the process would accelerate catastrophically. In the final tens of millions of years, dark energy would become strong enough to overcome the gravity holding individual galaxies together. The Milky Way would be torn apart. Its stars would be scattered into the expanding void. In the final months, stellar systems would be destroyed. The dark energy would be stronger than the gravity holding planets in orbit around their stars. And Earth would be ripped away from the sun. In the last few minutes, solid objects would disintegrate. Planets, stars, and even asteroids would be torn apart by the relentless expansion of space itself. In the final fraction of a second, the fabric of space-time would be pulling apart with such force that it would overcome the strong nuclear force that holds atomic nuclei together. Atoms themselves would be ripped apart into their constituent protons and neutrons. Then, even these particles would be torn apart into quarks. At the final moment, the expansion rate would become infinite. The very fabric of space-time would be ripped apart. Every single particle in the universe would be isolated from every other particle. The universe would end in an infinite and instantaneous tearing of everything. It is the most complete and total destruction imaginable. Whether this is our fate depends on the true nature of dark energy, which remains one of the biggest mysteries in physics. Number 3, a cosmic ray event can silently damage life. Cosmic rays are not rays of light. They are high-energy particles, mostly protons and atomic nuclei, that travel through space at nearly the speed of light. They come from violent cosmic events like supernovae, active galactic nuclei, and gamma-ray bursts. The Earth is constantly being bombarded by these particles. Our planet's magnetic field and atmosphere protect us from most of them. When a cosmic ray hits the upper atmosphere, it collides with an air molecule and creates a shower of secondary particles that rain down to the surface. This is a normal level of background radiation that life has evolved with, but what if the Earth were exposed to a much more intense flood of cosmic rays? This could happen if a supernova or a hypernova were to occur within a few dozen light years of us. The explosion would create an expanding shell of high-energy particles. When this shell washed over our solar system, the flux of cosmic rays hitting Earth could increase by a factor of hundreds or thousands. This would be a silent and invisible cataclysm. There would be no bright flash of light or massive explosion in the sky. But the effects would be deadly. The increased radiation would be a direct threat to life on the surface. It would increase mutation rates and cancer rates. More importantly, the cosmic rays would have a devastating effect on the atmosphere. They would ionize the air and trigger chemical reactions that would destroy the ozone layer. This would be similar to the effect of a nearby gamma-ray burst. The loss of the ozone layer would expose the surface to the sun's harmful ultraviolet radiation, causing widespread damage to ecosystems, particularly marine life like plankton, which form the base of the food chain. And the increased radiation could also damage our technology. Satellites would be particularly vulnerable, and the disruption to GPS and communication networks would be severe. There is some evidence in geological records, like isotopes found in ice cores, that suggest Earth may have passed through clouds of supernova debris in the past. These events are a more subtle kind of cosmic threat, not one of instant obliteration, but of slow, invisible poison from the sky. Number 2, a Wolf-Rayet star is a ticking time bomb. A Wolf-Rayet star is a very massive star, over 20 times the mass of the Sun, that is in the final stages of its life. It is an unstable, violent object. It has burned through the hydrogen in its core and is now fusing heavier elements. It is so luminous and hot that its own light exerts a powerful pressure, blowing its outer layers away into space. This creates a powerful stellar wind. The wind from a Wolf-Rayet star is much stronger than our sun's solar wind. It can carry away an enormous amount of mass, equivalent to the mass of the Earth every single year, at speeds of millions of miles per hour. This wind creates a vast glowing nebula of expelled material around the star. A Wolf-Rayet star is a supernova waiting to happen. It has already shed most of its outer hydrogen envelope. When it finally runs out of fuel and its core collapses, it will explode as a Type Ib or Type Ic supernova. Because the star is already surrounded by a dense shell of material that it previously ejected, the supernova shockwave will slam into this material. This collision creates an incredibly bright and complex light show. It is one of the most luminous types of supernovae. The interaction between the supernova ejecta and the circumstellar material can produce intense radio waves and X-rays for years after the explosion. One of the most famous Wolf-Rayet stars is Eta Carinae, located about 7,500 light-years away. It is an unstable and highly volatile system. In the 1840s, it underwent a massive eruption called the Great Eruption, where it shed at least 10 times the mass of our Sun and briefly became the second brightest star in the sky. This material formed the homunculus nebula that we see around it today. Eta Carinae is expected to explode as a hypernova sometime in the next few 100,000 years. When it does, it will be one of the brightest events ever seen in our galaxy's sky. It will be visible during the day and will cast shadows at night. It is a nearby, colossal, and beautiful time bomb. Number 1. Vacuum decay could erase the universe. This is the most terrifying and complete cataclysm that physics allows. It is based on the idea that the vacuum of space itself might not be stable. The universe might exist in a false vacuum state. Think of it like a ball resting in a small dip on the side of a large hill. The ball is stable in the dip. It won't roll away on its own. This is the false vacuum. But there's a much lower, more stable state at the bottom of the hill. This is the true vacuum. If the ball were to be given a push, it could roll over the edge of the dip and fall all the way down to the bottom, releasing a lot of energy. The same could be true for the universe. The Higgs field, which gives particles their mass, might have a much lower energy state than the one it currently occupies. It's possible that somewhere in the universe, a random quantum fluctuation could push a patch of the Higgs field over the energy barrier and into this true vacuum state. If this happened, it would create a bubble of true vacuum. Inside this bubble, the fundamental laws of physics would be different. The properties of elementary particles, like the masses of electrons and quarks, would change. The constants of nature would be different. The very structure of matter as we know it would be impossible. This bubble of true vacuum would expand outwards in all directions at the speed of light. As the wall of the bubble passed through a region of space, it would instantly rewrite the laws of physics. Everything in its path, stars, planets, people, would be obliterated without any warning. You would not see it coming because the leading edge of the destruction travels at the speed of light. One moment, the universe is as it is. The next, it is gone, replaced by a new alien physics where our form of existence is impossible. The universe would be eaten from the inside out by this expanding bubble of nothingness. This is vacuum decay. It is a purely theoretical idea, and most physicists believe our vacuum is probably stable. But we can't be certain. It is the ultimate unpreventable cataclysm. It would not just destroy the Earth or the galaxy, it would destroy reality itself.